the DE0-Nano is a very low-cost board with a Cyclone 4 FPGA. But it's also got some other interesting hardware on board, including a 12-bit A to D converter. And this gives us a chance to practice writing SPI interface code using the FPGA, using Verilog hardware description language to interface to this A to D converter. And once you've got the hang of this one, I'm fairly sure that you'll be able to write SPI interface code for any A to D converter. So let's give this a go and see how far we get. Before we get to the specifics of our device, let's look at the big picture. Now, the role of an A to D converter is to convert a sampled analog waveform into a digital equivalent. And you can see here this device uses 12 bits. Now, the more bits you have, the finer the resolution in which you can represent an analog sample. But there are actually two types of A to D converter. One of them sends out these 12 bits in parallel, so they all come out at the same time. The second type sends out the bits in series. So you get one bit at a time, and your interface code has to work out a way of picking out these bits at the right time to form your 12-bit word. The big advantage of this serial type of A to D converter is that you don't need so many pins. In fact, to read out each conversion, you need just a single pin. Now, typically, you'll also need to program the A to D converter, so there's normally a pin dedicated to this. And again, you write bits in series. You also have a chip select or start conversion pin. And importantly, you also have a clock. And that clock kind of coordinates everything. And the key thing to remember with this kind of device is that timing is really important. So, you have to pick out the 12 bits at exactly the right time to form your conversion word. And similarly, to program the device, let's say to choose the channel or the acquisition mode, you need to write in those bits at exactly the right time. So the clock, the S clock, is important because it allows you to coordinate this activity. Now, hopefully this will make a bit more sense when we go to the timing diagram for the device that we'll be using. Okay, so here we are with the part of the datasheet for the ADC 128S022. This is the A to D converter that's on the DE0-Nano board. It's an 8-channel 50 kilosample per second to 200 kilosample per second 12-bit A to D converter. We've got the pin map here, so this might become important when we do some probing later on. With the oscilloscope. But the important page for us at the moment, if we want to write interface code for this chip, is the timing diagram. So typically this is where you would go first. This basically tells you everything you need to know to write the interface code. And you can see we have those 4 pins that we talked about earlier. We have the chip select pin, so that will go down, and on the falling edge that will initiate the start of the conversions. Then we have the S clock. So the S clock frequency, you have to be careful here because there are limitations on the maximum frequency that you can have for the S clock. So I think for this chip, it's a 3.2 megahertz, upper limit on the S clock frequency. Then we have the D-in, so this is the programming pin for this chip. And you can see it's actually quite limited on this chip what you can actually program. So, all you can do here is actually choose which channel currently taking a sample from based on the value of these bits at this time in the S clock. Then we have the D-out. So this is where the 12-bit conversion word for the current sample is read out, and this comes out 1 bit at a time. So we have to be really careful in the interface code that we pick these bits off one by one, and we have to know exactly when they're coming. And the way that you know is you look at where you are in the S clock. So we can expect bit 11. We can expect that to come out, well, it will start on the falling edge of the 5th S clock, but really we should be reading this on the positive edge of the 5th S clock. So that's when we look at what the value of this bit is, and then we basically register that value into our 12-bit word. And then we do the same for DB10, that's on the 6th cycle of S clock, and then so on. And we build up our 12-bit word one by one. Now for the programming bits, as I said before, this determines which channel we're looking at on the chip. You can see we have 8 channels here, so you can put analog signals into all 8 of these channels if you want, but the A to D converter needs to know which one you're looking at basically. And from the table in this data sheet, if we're just looking at channel 0, we can set these to 0, 0, 0, and then I think 0, 0, 1 is channel 1, and so on. But that's basically it. That's all there is to this. So I think we're ready now actually to make a start with our interface code. Let's just remind ourselves of the sequence of events that we need to cater for in the interface code. And I've made an animation for this. So this is the analog waveform. We sampled this at 200 kilosamples per second. Now let's say we zoom in to this blue box. So we're within the time scale of just a single sample. And now we can see things happening at a much faster rate. The sequence of events is as follows. We have the chip select pin go low, which initiates the start of the conversion. Then we have the track time for the ADC. And then we have to make sure in our code that we write the appropriate values to the input D-in pin and read out the bits one by one as they come out of the D-out pin. You can see I've numbered here the S-clock cycles. We have to make sure in our code that we keep track of where we are in the S-clock cycle. And you can see we get 16 counts of S-clock. And what we can do actually is just have a 16 count, that's a 4-bit free running counter, which just repeats itself. So it goes from 1 to 16, and then it goes back to 1. And that will be appropriate for us because we can just keep the conversions going. So this is what we plan to do. So we want to write a Verilog module for the interface code. We want to write a test bench and simulate the interface code. Then we'll create a BDF, import our working interface module and apply a clock. Of course, we need to assign the correct pins, program the DE0-Nano board, and then we can check whether it's working by using Signaltap. And then we'll rewrite the code to accommodate multiple channels, not just a single channel. Here I am in Quartus. I've started a new project, and you can see in my device settings, I've made sure I've selected the correct code for the FPGA on the DE0-Nano board. But now it's time to start writing the interface code. And as I said before, my workflow will be to first of all write a basic version of the interface code. Then I'll simulate using Model Sim, and then I'll slowly progress this to implementation on the board with the help of Signaltap, which is a really nice debugging tool, because you have to work out if the FPGA is actually doing what it should be doing. So Signaltap allows you to basically see the signals in real time inside the FPGA. So first thing I'll do here is go to File, New, Verilog HDL file, and I'll start a new module. And I'll call this module SPI Interface. And initially, I'll just make sure my input signals, I have a clock coming in, I know I'll have D-in coming in, and I know I'll have D-out coming out of this interface module. They're the basic signals that we need. And there's actually one I forgot. We also need the chip select pin. So I'll go ahead now and just define these as inputs and outputs. So D-in is an input from the A to D converter. We have an output, D-out, which is just a 1-bit output. And then we also have an output, chip select, which again is a 1-bit output. Now, if we take a look at the timing diagram, we note that the way things happen is kind of in a 16 count cycle. So the first thing I would do here is make sure that I had a counter, a 4-bit counter, which will help basically to regulate all the activity. And the good thing is, because it's a 16 count cycle, we can have a free running counter. So we can just set it up as a 4-bit counter, 1 to 16, and then it'll roll back to the beginning again, or 0 to 15 actually. Then it'll roll back to the beginning and just repeat with a cycle of 16. So that's going to be the first thing I do. And to do this, I'll just make sure I have a 4-bit register called count. I will initialize this register to starting value of, we might as well start it as 0. And then in Verilog, it's really easy to do a free running counter. So we just do always at positive edge of clock, and we just make sure that the count using a non-blocking assignment will increment by 1 at the positive edge of each clock. So that will give us a 4-bit counter, which will go from 0 to 15 and then just roll back down to 0. So that's fundamentally that's a key part of this interface code. Now let's take a look at this timing diagram. Now the first thing I'll do is look at this chip select. And you can see that chip select starts off at 1. So what I'll do is in the initial, I will initialize chip select to 1 because we know that's where it will start. But note how chip select initiates the start of the conversions on the falling edge. So what we need to do is find a way to make chip select go to 0, but we want this to be controlled, and we also want it to sort of correlate with when the S clock starts going, okay, because the S clock also starts at 1. And my plan here is actually to, we know that the clock is coming in, that clock is going to be at 3.2 megahertz if that's the S clock frequency that we're going for. And what I want to do is make the value of S clock take on the value of clock in a controlled way. Okay, so what I'm going to do is make chip select go low, and at the same time as chip select going low, I want S clock to begin taking on whatever the clock is. In some ways, what we need is something similar to an if statement for S clock, and we say if chip select is 1, then S clock is 1, or if chip select is 0, then S clock is equal to clock. But first of all, let's deal with chip select. So what I'm going to do is to start off chip select as 1, and then I'm going to have another always block, and I'm going to say if count is equal to 1, then I will make CS go low like this. This is controlled by the value of count. Now you can also make this controllable via a push button or another Verilog module, but we'll keep it simple for now. Okay, so I've just added an S clock here as an output register. That's one that I forgot to put on the list here. So I think we're just about ready to finish the first step of this development. And what I'm going to do next is actually simulate what we have at the moment. And the reason I'm simulating so early, because we're nowhere near finished with this interface code, but the reason I like to simulate early is twofold, really. The first reason is it gets your test bench ready. And the second reason, it allows us now to take an incremental approach to the rest of the development. And believe me, with something like this, it might not be the most complicated piece of code. There are some headaches that we have to solve in terms of the relative timing between signals. So we will have to reiterate our code and go back into Model Sim. An element of it is trial and error sometimes. You can't get away from that. But this is what we have so far. So what I've done is I've made a test bench. So just to avoid some nasty numbers here, I'm going to go with a 1 megahertz clock. This is going to be a 500 nanoseconds, so every 1000 nanoseconds, that will be one period of the clock. We can always change that later. But we've instantiated the SPI interface module that we've built here. So .clock, that's taking the clock. .sclock, so we've defined that as a wire. Nothing is actually happening here. I've just realized if we run this, we wouldn't get any signals out. But the thing we're interested in is actually the value of count at the moment anyway. I mean, this is just the start. So what I'm going to do is just make count an output register. Okay, so I'll make count an output register, and that will make it easy for us to monitor the value of count within Model Sim. So I'll just go ahead and add count into the list here and just make sure that we generate a 3-bit wire called count. We can actually call it anything we want within the test bench, but tell you what, just to make it the same as all the other test bench signals, I'll call it this. So that's basically our test bench for now. So I'm going to go ahead and run this code. I'm going to set the test bench as the top level entity. I'm going to go into assignments, settings. Okay, this is one of the hoops that Quartus makes you jump through to get a simulation going. So we go to simulation, compile test bench, test benches, new test bench. Our test bench is called test bench. And then we have to select the .v, add, and now that's nicely set up in the native link settings, which will allow us to open ModelSim straight from Quartus. Let's just make sure we set the test bench as the top level, and then we'll go to analysis and elaboration. So as always, we get a few errors. So the first one, I was missing a semicolon. Okay, just ignore that. So next error, so cannot connect instance port. So I think well, that should be a dot. This is the common kind of error that you get sometimes with Quartus. So I'll try again. So this time we've had a bit more luck. So I think we can now go to Tools, Run Simulation, Tool, RTL Simulation, and now ModelSim should open. So this is the simulation results in ModelSim. So what we're looking for is just the value of count. So what I'll do is just right click this, change the radix to decimal, and there we can see, well, if we make it unsigned decimal, that would be even better. And we can see that count is incrementing from 0 to 15 on the positive edge of the clock. So first step is good. We can also check on the chip select, and that goes low at the right time. So we can move on to the next stage now. Now, I mentioned before that I want the S clock to start off as 1. So S clock should start out at 1, and then I want it to take on the value of the input clock when the chip select pin goes low. Okay, and remember, the input clock is just going to look like a clock at all times, but we want the S clock to start off at 1, and then only when the chip select goes low do we want the S clock to basically mimic what the clock is doing. And one way we can do this is to have the clock coming in, and we can have a kind of an if statement looking at the value of chip select. If it's 1, then make S clock 1. If it's 0, then we wire the input clock to S clock. And I'm actually going to change S clock to a wire here just to make our life easier, and then I'm going to use this assign statement. Okay, so I'm going to say assign S clock is equal to chip select question mark, and that's saying basically what's the value of chip select. If chip select is 1, S clock is assigned the value of 1, otherwise S clock is assigned clock. Okay, so this is a shortcut way of doing a sort of an if statement. So this is kind of a one-line trick, a very concise way of writing this expression. And hopefully this should give us exactly what we want in terms of the S clock taking on the value of the input clock when this chip select goes low. So let's give this a go. We'll run the test bench again and we'll see if this works. So this is the ModelSim result, and you can see it's kind of working because we have the S clock here. Now when the chip select goes low, we can see that the S clock begins to take on the value of clock. But it doesn't quite look like the timing diagram in the datasheet, because what you'll notice is it's not instantaneous. So what we really want is for chip select to go low, and we want S clock to go low straight away, because the chip select is being updated on the positive edge of the clock. Now, if we change this to happen on the negative edge of the clock, so when count becomes 1, the chip select should go low on the negative edge of the clock, and that should give us the behavior that we're looking for here. So let's try this one, and then we'll resimulate in ModelSim. And here's the updated model sim results, and you can see now this is the behavior we're looking for, because the S clock will begin to take on the value of clock on the negative edge of the clock when the chip select goes down. That's exactly what we want, so we can push on with the design. So where do we go next with this? I think it's time now to start looking at what we do with the D out and the D in pins. Remember, with D out, this is the information which is coming from the A to D converter into the FPGA, into our interface code, basically gets a series of bits. So it starts off with the most significant bit of the 12-bit word. Now that comes out, the timing diagram tells you exactly when this comes out. Okay, so it's on, well, we look for it on the rising edge of the 5th S clock, and they come out one by one, and our interface code has to pick these out at the right time, then construct this 12-bit word. Now D in, that's the programming bit which is coming from our interface code into the A to D converter. And remember, the value of those bits will determine which channel the A to D converter is sampling from. And remember, channel 0 is 0, 0, 0 for ADD2, ADD1, ADD0. And there's a table which tells you what these bits should be to give you the appropriate channel. But again, we have to get the timing right on this. Okay, so those bits have to change at the right time. Okay, so we've got two potentially tricky challenges here. Now we'll simulate, we'll do, we'll have a shot at this code and simulate, but I will warn you, once we get to the FPGA and implementation on the FPGA, it doesn't always work as you see it in simulation, and there is an element of trial and error. But this is why a tool like Signaltap is so important. But anyway, let's adapt this code and let's see how we can tackle this problem. Now, if we take a look at the timing diagram again, we can see that we need to take action on the positive edge of S clock. Okay, so if we start with D out, so remember this is the 12-bit word coming into us from the A to D converter, we'll see here that we need to register these input bits on the positive edge of the S clock. That's something to bear in mind. But we also look at D in. D in is defined as the programming bits to the A to D converter. So this is signals that we need to make in our interface code and then send out to the A to D converter. And we can see that we need to change these values on the positive edge of the clock, of the S clock. Both things need to happen on the positive edge of the S clock. That's hinting to me that we need an always block with the positive edge of the clock, and then we can take care of both of these things, maybe potentially in the same always block. I've made a bit of a mistake here, because D in should actually be an output. Okay, and I'm going to define this as an output register. Similarly, D out should actually be an input. Okay, so that's coming into us from the A to D converter. But let's start here with what we do for D in. Okay, I'm going to paste some code in, and what I've got here is an always block, so always at positive edge of clock. We're looking at the value of count, and as a first guess, what I'm going to say is if count is equal to 3, so positive edge of clock, count is equal to 3, what I'm going to do is I'm going to make D in take the value from ADD2. Then when we get to 4, we'll take on the value of ADD1, and then when we get to 5, we'll take on the value of ADD0. To make this work, these values here are registers, they're kind of variables, and what we need to do is just define these signals in our code, and then we can initialize these to whatever we want. Okay, so I'm going to start them off at 0. In fact, I'm going to make the middle one 1, just so when we simulate it, we can kind of work out where we are and if we got the timing right. But doing it this way just makes it a bit easier for us to change these values later on if we need to. Okay, so again, I'm going to take an incremental approach. So what I'll do now, before I even think about doing D out, I'm just going to make sure that this is working, and then we can make another step forward. So I'll just move to Model Sim, I'll run analysis elaboration again, and then go to Model Sim. So just very quickly, I've made I will make a modification to the test bench. Now we've made DIN an output reg. Because it's an output of a module in our test bench, we need to make it a wire. And the input to the module, which is in fact DOUT, is a reg. This is what will change a bit later to be the input to this module. But for now, I'm going to go to save, and I'm just going to do analysis and elaboration again, and then we can open this test bench. So here's the model sim results, and you can see DIN. Remember, we've set the middle of the 3 address bits to 1 to check its alignment with where it should be relative to the count. And you can see it goes high on between the 4th and the 5th S clock. That's roughly where we want it to be. Okay, so I think we can now go ahead and move to the DOUT pins, but it's actually difficult now because DOUT is what's produced by the A to D converter. So we've kind of hit a roadblock now. We can't really make much more progress until we actually program the device, apply a signal, and then check to see what we have in Signaltap. So at this point, I'm going to say that's probably enough for the simulation, and I think we can now move forward and actually do move the development towards implementation on the actual device. So let's go ahead with that. So I'm going to go to File, New, and I'm going to do a new block diagram schematic file, a BDF file. The good thing about doing a test bench and at least partially testing it is that we know we have a semi-working module here which we can drag into our BDF file. So to do this, I'm going to right click on the .v and I'm going to select create symbol file for current file. That will produce a block. Then we can double click somewhere in our BDF and our block should be in project. So that's our block. What we need to do now is generate an input clock. So we're going to have our clock coming in here. We have DOUT here. So that's an input into our interface code, and that's going to carry with it the ADC 12-bit result coming in series. And then we have the outputs of the interface module, which of course S-clock, DIN, chip select, they are the signals which need to go out into the A to D converter. So we've got some pins to put in, but first of all, I'm going to make the clock. So I'm going to go to Utility Windows. I'm going to go to IP Catalog, and I'm going to look for a phase locked loop. This phase locked loop, Alt PLL, give it a name, and I'm going to configure this phase lock loop for an input signal of 50 megahertz. That's the crystal clock frequency on the DE0-Nano board. Of course, that's coming into the phase lock loop, but we can configure the output of the PLL to a custom frequency. Now, we don't need any asynchronous reset or any locked output, but what we do need is an output clock. The output clock that we want is 32 megahertz. So let's see if 3.2 megahertz. Let's see how close we can get, and that's fine. We're going to get 3.2 megahertz. So next, finish, and I think I should have selected that to make a block for us, but it doesn't matter. I can just right click and I can create symbol file from the .v to give us our clock. But let's save the BDF first. I'm going to save it as block, and now it will make a block for our BDF. So I'm going to go back to the BDF. Sorry, trying to work in a small space here. Now if I double click, you'll see that the PLL is there. I'm going to drop that into my design. I'm going to wire the output of the PLL to the input of my SPI interface, and now I'm going to put some pins in. So we know we need an input pin for the input clock, and we need an input pin to DOUT. We also need some output pins, so I'm going to do 1, 2, 3 output pins for S-clock, DIN, and chip select. So now it's just a case of wiring these up. So let me wire these up and I'll come back when that's done. So here's the BDF now with the input pins and the output pins. So what I can do now is set the block as the top level, and then I will go to analysis and elaboration. And once that's finished, with the BDF as the top level, we've basically transitioned our workflow to programming the actual FPGA. So just as a quick recap, if we want to simulate, we put test bench as the top level. If we want to program the board, we put the block or the BDF as the top level. So once analysis and elaboration has been completed, we can then do the pin assignments. So we go to assignments, pin planner, and then now it's a case of going to the user manual for the DE0-Nano board and just making sure we put the right assignments in here. So I'll just go and check what those pin assignments are and then come back. So if you are following this at home, here are the pin assignments. So we've got the input clock is R8, and then we have the other pins assigned here. So this information is available in the user manual for the DE0-Nano board. So I'll just close that one, go back to our design, and now it's time to do compilation. So I have compiled, that was successful. So what I'm going to do next is see if we can program the board using Signaltap. And the reason Signaltap is so useful in this kind of scenario is because it gives us visibility inside the FPGA. So for something like an A to D converter, this is invaluable because we get to actually plot the signal in real time. Now, without Signaltap, this is very tricky. You have to do some, you have to do some custom logic to, and send the signals out. It's just trickier. So let's see if we can open Signaltap. So if I go to Tools and then I open Signaltap Logic Analyzer. Now let me just bring the window in. At the moment, there's nothing here. So what we need to do is, first of all, find the device. I've currently got the device plugged in. I've got the USB blaster, so it finds our device straight away. But what I need to do now is, first of all, select a clock. So the clock is important in Signaltap because that's what triggers the event. So when we see the waveforms, it needs to be triggered by something. So what I'm going to do is select the clock, and I'm going to select Signaltap pre-synthesis as the first attempt. Now if I hit list, we get a list of our signals, and the one I'm going to select is this one, the 3.2 megahertz clock. That's what everything else will at the moment trigger off. Now for the sample depth, we want maybe 4K. Now there is a trade-off with the amount of memory that you have in the device, but at the moment we're not using anything in terms of the built-in memory of this FPGA. So 4000 sample depth, that's probably safe. And now we select the signals. So again, I'm going to select pre-synthesis, and it does a search for all the available signals that we can look at. So I'm going to go into the SPI interface. I'm going to look at count. I'm going to put that one in. Definitely going to look at S-clock. I'm going to look at D-out. I'm going to look at D-in. I'm going to look at chip select. There's no point looking at clock because that's going to be same as the trigger. And I think that's okay for now. So I'm going to insert these signals in. They should go into the window. That's it. So sorry, you probably couldn't see that, but they're the signals that I selected from Signaltap. Close, and now we have to recompile. That's one of the disadvantages of Signaltap. Every time you make a change, you need to recompile. So let's hit recompile, and I'll come back when this has finished. So time to go full screen, I think. So when you've finished the compilation with Signaltap, you just need to select the output file here. So if you go here, select the output file, it might be in output files, but you get the .sof, and that will have the Signaltap enabled. Once you have that, you can just hit program device, that will program the device, and then you can auto run analysis by hitting that button. And you can see this gives us a really good insight into what's going on. So this is actually real-time signals within the FPGA, which we have visibility of because of Signaltap. And you can see we have, I'll just pause it here, we definitely have the count. So what I might do is just change the display format to unsigned decimal, and we can see that's definitely going from 0 to 15 and then back to 0. D-in, well, that looks very much like our test bench, doesn't it? So that's encouraging, but we also have D out here. And what I'm doing is I'm applying a 6 kilohertz signal at 1 volt peak to peak with an offset of 1.6 volts. So we should see D out vary. So, but I'm not actually sure I've got this in the right channel. Let me just check what channel I'm actually applying the signal to, because actually the channel that this is sampling is going to be affected by the fact that we have ADD1 set to 1. So it might not be the channel that I've currently got it connected to. Let me just double check. Okay, so this is interesting. I've actually changed the input channel now to channel 0, and it seems to be that the input channel that it's sampling is actually channel 0. Okay, and I know this because I've changed my input signal to a DC, and I currently have it as an offset of 0 volts. So we should see absolutely nothing at the moment, and that's exactly what we see on D out. But watch what happens when I start increasing the DC value on this A to D converter. You can see now we have a signal coming out of D out. That's 100 millivolts. This is 200 millivolts. 300, 400, 500, and you can see that signal changing. So let's just recap back in the Verilog code. What we've just observed is when ADD1 is 1 and ADD0 and ADD2 are 0, we're seeing channel 2 is being sampled. So what this is telling us is this is lined up correctly. So what we can start thinking about now is reading out the bits from the A to D converter and forming our 12-bit word. Okay, because at the moment, if we look at Signaltap, the bits from the A to D converter are coming out in series. So we need to work out where the first bit is, where the second bit is, and we need to, one by one, construct a 12-bit word. Okay, so that's the next challenge. Okay, so I'm going to paste some code into our SPI interface module here. You can see it's another always block. Okay, so we have always at positive edge of clock, okay, because we know that the D out should be registered at the positive edge of the clock. That's what the time-in diagram is telling us. So that's exactly what we do in this always block. Now you'll note I also have something else going on in here. Okay, so we've got a clock out signal which goes to 1 approximately halfway through the cycle. And the reason for that might become more clear when we go back to Signaltap. Okay, well, just to give you a preview of why this is necessary, what we would like to do later on is basically sample this signal not at the SPI clock rate, but at the same rate as the samples are coming out of the interface code. And basically we get one sample every 16 S clocks. So if we create a clock and we make that clock transition, basically go to 1 halfway through the cycle like this, we can use this to trigger Signaltap to basically tell us what the value of data route is at that time. Okay, so that's something we'll do later. But just to look at this again is a case statement, and we're looking at, when the value of count is 6, that's when we will register D out into this array. So data temp is the array. So the most significant bit is being registered, the value of D out when the count is 6, and we just keep on going until we've filled up all 12 bits of data temp. When all 12 bits are registered into data temp, we take that value of data temp and we register into a different 12-bit variable called data out. And data out is the one that we will be looking at in Signaltap, and that's the one that we can basically plot our signal from, registered on clock out. Okay, so I hope that makes sense. So I just need to create these variables and just make sure everything is correct. So basically data out is another register. Okay, so it's an 11-bit register, and we also need temporary register called data temp. So it's the same thing, still a register, but this one is called data temp. And we also need a new register called clock out, and this is just a 1-bit register. Okay, and let's just make sure we initialize these to a starting value. So data out will be 12.0 and data temp will be 12.0. and we need to make sure actually that data out is an output, because we want to view this as an output of the interface code. So I need to make data out an output register. So I think that's basically it for now. So let's save and we can then recompile. Okay, so that's finished compilation and we're back in Signaltap. I'm applying a 1.7 volt DC signal here, and you can see there's something not quite right, because what we would expect is, if the reference voltage on the A to D converter is 3.2 volts, so 1.6 volts would be half range. So we would expect the most significant bit here to be 1, but what we can see here is we're not quite getting that. So if I pause this again, now we know that D in, this is for channel 2, so we can kind of guess that that's not quite aligned as it should be. And I think if we go back to the timing diagram, ADD1 would be there, and you can see we already have some signal there, and I'm just wondering if that is the most significant bit. That's likely to be where it would be. So there's a problem with reading these signals in, so let's just go back to the code and see if we can align this a bit better. Now I've got it going in at count 6 here. Now maybe that should be going in at count 4. So I'm going to change the first one to count 4, update the rest, and then see if that makes a difference. So that's the updated statement, case statement here with the new numbers. So I'll recompile. So this is the updated Signaltap results, and we can see we're almost there now, because you can almost map out, because that's 01001, so you can see the pattern here. So it must be picking out this point, this bit here first, when it should be picking out this bit. But you can see the pattern, it's 100100111100. Now the only reason I know what this should be is because I know that this is over halfway in the range, so I know that this must be the most significant bit. Now there is, you could do this more scientifically if you go to the timing diagram and you compare it with what we have for D in, because we know that's channel 2, so we know that must align with ADD1, but trial and error. It's another way to do it. So I'm going to go back and just make this adjustment, and then we'll come back and see if that works. And the adjustment I made was just to increase the count by 1, so it picks up that bit just 1 clock cycle later. So I'm back in Signaltap here. I'm applying a 2.2 volt DC signal, and if I just pause it here, you can see that I think data out is the correct value now. So you can see the pattern. This is D out 1010101101, and that is approximately what we're getting. Now if I just move the DC input to below 1.6, so this is below VREF divided by 2, we should see the most significant bit go to 0, because now we're halfway below the range. And if I pause it here, you can see that's approximately correct. Now what I'm going to do next is just grab my camera, and I'll just change the wave shape to a sinusoidal wave shape. But what I need to do is set the offset to 1.6, so that's VREF divided by 2, and then I can set my if we just choose a 200 millivolt RMS sinusoidal wave, and the frequency 1 kilohertz. So let's see what effect that's had if I just play again. And now what we can do is, if I right click data out and I go to bus display format, unsigned line chart, you can see we are seeing some kind of wave shape. If I increase the frequency, you can see we're seeing a sinusoidal wave, which is exactly what we want to see. Now let me quickly change this to a square wave. Yeah, that looks a bit like a square wave. But now the problem we run into now is we don't have enough samples to really see this wave properly. Okay, and the reason for that is because Signaltap is being triggered by the S clock, which is much faster than our sample rate. So if I just zoom out, you can see we're taking 16 samples per output sample from the A to D converter. So what we need to do is go back to the code and make Signaltap trigger off a signal which is much slower. And in fact, if I go back to Signaltap, we look at our SPI interface, you can see we've already got this signal clock out. And I talked about this earlier. The reason I put that in is because it now gives us an option. If we look at the rising edge of clock out and then sample data out, that will trigger at a much slower rate, and the rate will actually be the same as the output samples from the A to D converter. So we should see much more of the waveform. So let's recompile Signaltap, but this time we'll put clock out as our trigger. Okay, so I've now added clock out as the trigger in Signaltap. And just to make this clear, what I needed to do was to make clock out an output from the module, because Signaltap in pre-synthesis mode wasn't finding clock out. It was being synthesized away. So if you put it as an output signal from the module, we don't intend it to go anywhere, but it just makes it easier for Signaltap to basically find it. So let's go back into Signaltap. So now we have clock out as the trigger, and now that is going high at the same rate, the same frequency as our samples are coming out of the A to D converter. Okay, so now we get to see much more of the waveform. So you can see here I'm applying a 12 kilohertz signal. Note that D out and D in, these are meaningless now because we're sampling at a much slower rate than the S clock D out and D in are coming out. So that's meaningless at the moment. So don't bother looking at these signals. That's just meaningless. But what we can see is the output waveform, well, much more of the signal. Okay, so that's 12 kilohertz. I can decrease the frequency. That's 5 kilohertz. I can increase the amplitude, so now we can go up to 5, 6, 800 volts RMS, peak to peak. I can change it to a square wave. Okay, that's good. Ramp, pulse, and so on. So I'm fairly happy with this. Now this is sampling on channel 2, okay, but I'm satisfied now that this is doing what it should be doing, and I'm satisfied that the interface code that we wrote might have taken a while, it might have taken some trial and error, it might have taken some repeated attempts, but we got there in the end. And you can see this is sampling on channel 2. This is exactly what we would expect for 010 on these ADD on the DE pin. However, if we wanted to change the channel, and well, I guess the common situation would be if you wanted to sample on more than one channel simultaneously. That's the next challenge, and that's what I'm going to do next. So if we go back to the interface code and we look at the timing diagram again, we recall that the channel that is being sampled by the A to D converter depends on the value of these ADD0, 1, and 2 values at the appropriate time in the timing diagram. So at the moment we have it set so we have 0, 1, 0, and we've made sure that that's the case by using this always statement and a count, and we verified that 0, 1, 0 here does indeed give us an input on channel 2, and all the other channels give no output from the A to D converter. So if we want to change which channel the A to D converter is currently looking at, we need to change these values. And it does get a bit complicated because if we want to look at more than one channel at once, so let's say we wanted to sample channel 0 and channel 2 at the same time, we would have to dynamically change these values between cycles. Okay, so for one cycle, so 16 cycles of the S clock would give you one cycle. So for that cycle, you would look at channel 0, but for the next one, you would have to dynamically change the value of these bits to change which channel the A to D converter is looking at. So that makes it a bit complicated. One way that we can do this is by changing the value of ADD1 on each cycle. So basically inverting this bit. So if we start off at 1, that will look at channel 2, and then we can have somewhere within our code, we could have maybe a command which inverts this bit, so it turns it from a 1 to a 0. So for the next cycle, it will revert to channel 0. So that's one way that we can have the A to D converter looking at channel 2 for one cycle, and then channel 0 for the next cycle. Now, it's important to note here that we can't look at two channels or more than one channel simultaneously, but we have to do it by cycle. And what we're effectively doing here is cutting the maximum sampling rate that we can have for the A to D converter. So currently we only have one channel, so we can have the maximum 200 kilosamples per second. But if we have two channels, it cuts down to 100 kilosamples per second for each channel, because effectively now we're only taking one sample every 32 S clocks rather than every 16 S clocks. Let's see if we can adapt this code so we can look at more than one channel. Now, at the moment we have this variable data out, and what I'm going to do is make a second variable called data out 2, and that will hold the value of the second channel. Okay, and I'm going to use an if statement which looks at the value of ADD1. So if ADD1 is 1, then we will put data temp into data out. If it's 0, we will put data temp into data out 2. So let me take a second to adjust this code, and then we'll come back and have a look at it. Right, so I've made some modifications to the code. So first modification I've made is now added a statement here which inverts the value of ADD1 on count 5. So that's after ADD1 has been registered for that cycle. We change it so it's inverted, so the next cycle the other channel will be sampled. So that's the first big change that's been made. The next change is in the main always block here, which is registering the inputs from the A to D converter into the 12-bit word. What I've done on count 4 is I've looked at what the value of ADD1 is for that cycle. If it's 1, we register the temporary word which has been picked off bit by bit from the bits coming in. We put that into data out, otherwise it goes into data out 2. So data out will carry one channel and data out 2 will carry the other channel. So we should be able to see the output from both channels in Signaltap, and this code should be reading both channels at a reduced sampling rate. So let's go over to Signaltap. I've already programmed it here, and you can see I'm applying if I just get the camera, I'm applying to channel 1 3.6 kilohertz, so that's one of the channels, and the other channel is a 6 kilohertz sine wave. So we can see roughly that's what we're getting. So if I decrease the frequency of the first one, there we go, 3, let's go to the other one, 3.6, make them the same. Now if I change the amplitude of that one, then they look roughly the same. So in terms of the board, you can see I've got both channels of the signal generator being used, and they're going into both channels into the A to D converter at the same time. And we can make one of them a square wave, one of them a ramp. So I'm pleased with the progress so far. There might be some bugs to iron out, but hopefully you enjoyed that video. So we walked through step by step how to write SPI interface code for the A to D converter on the DE0-Nano board. It seems to work fine. As you recall, we started off simulating. That's a good habit to get into, but we very quickly transitioned to the use of Signaltap. And I think I've demonstrated here the usefulness of a tool like Signaltap, because without Signaltap, well, what could we do? I mean, one solution would be to output these waveforms on a DAC, but I don't have a DAC. So Signaltap is an amazing debugging tool. If you're not already using it, I would highly recommend you develop some expertise in it, because it will expedite your FPGA development. So thank you very much for watching, and I'll see you in the next video.